Hello, good afternoon. Thanks for joining. I'm just giving a few minutes for people to filter in. Hopefully you can see my screen and hear me. I'll also be using the text chat, the remote hardware text chat up here. I'll just send a message up there as well. So just drop a g'day up in the remote hardware text channel if you're going to be joining, and hopefully you can all hear and see. We'll just give a few minutes for people to come and join. I know there's been a bit of checking if I'm recording and stuff, so I think it probably runs into different workshops and stuff for other courses and whatnot. So we'll give it a bit of time and see who's going to join. But hi, thanks for coming. I'm John, and yeah, we'll be running through some MATLAB today. Can I just check? Do you guys have a copy of MATLAB ready to go? Hopefully, I'm using MATLAB. I think it's release 2019B. There's plenty of different releases of MATLAB that you can use. They should all be good to use. There's nothing particularly fancy or new required for all of these, but yeah, generally you can get a late release from the university student releases, which is good because MATLAB is quite expensive. So got a few people filtering in now, so that's excellent. And yeah, I am recording on my end. It's just going to be my screen though, so unless you guys end up sharing screens back, I don't think you will be particularly recorded, but I should just let you know that potentially you will be recorded. And yeah, just a bit of general remote etiquette. Please remain on mute if you're going to be hanging out in the voice chat. More than happy for you to say hi. But yeah, just managing a lot of people in a text and a voice chat can be a little bit cumbersome, as you're all probably aware of from all your remote workshops and stuff. So, hey Rick, I'll just get you to mute if you're there and not going to be talking. Thank you. But yeah, feel free to say hi while we're in this pre-stage. I'm yeah, doing my masters at the moment. Only one course. Pretty laid back. I'm keen to keep these remote workshops relatively casual. Hopefully a little bit more casual than you've been used to with your coursework remote workshops. They can be a little bit awkward at times, so feel free to break the ice, say hi, jump up in the text chat. Let's get that going as well. That's in the remote hardware text channel up there, so say hi up in there. Yeah, let's keep it casual, not too worried. Yell out as usual if anything comes up, or if suddenly my screens stop or you can't hear me anymore. Yeah, let me know. We'll give it a few more minutes. There'll be a mix of sort of me working through stuff and a little bit of exercises for you guys to work through too. with MATLAB on your end. So there's a bit of a range of stuff, but there is a lot of content, a lot of stuff to cover. So I'm going to be motoring a little bit. I aim to finish by 7:30, hopefully a little bit earlier. But yeah, there's a bunch of content to cover. There's a fair bit. So yeah, we'll get through some, and yeah, yell out if anyone doesn't understand anything. There should be sort of a good amount of people for solving specific problems if they do come up. So feel free to yell out if a particular issue arises. I can help you individually. You know, if it gets above 15 or 20, that can be a little bit awkward, but with this sort of number, it should be manageable. I'll get going at probably about 10 past, guys. So. Might be worth also, I might throw the slides up for you as well, share them with the text channel directly, particularly as I'll be working in the actual MATLAB window. It can be a bit difficult to see the slides at the same time, so just give us a second, I'll get those up for you. All right, they should be up for download in that text channel. Workshops do run mostly weekly. We'll hopefully get a master schedule out at some point. They're not all MATLAB though, so they are varied. So first week is MATLAB. The first 3 weeks are sort of MATLAB centric. This week's MATLAB. Next week we've got a Simulink workshop, and then the week after that I'm running an advanced MATLAB workshop. So if you're keen to really get into MATLAB, probably these first 3 weeks will be really useful for you. And then the other sorts of workshops that we've got, I'm running a LaTeX workshop. I'm going to do a control systems workshop. What else am I running? I've forgotten a little bit. I think there's a Git workshop later on. If you're interested in Git and programming, that's a really useful tool that I'll be running. So there's a bit of a varied selection of types of workshops that I'll be doing. So, but certainly the first 3 weeks are a little bit more MATLAB centered, and yeah, particularly you're going to be using MATLAB so much if you're in engineering. So it's good to really get a handle on it. All right, so we just hit 10 past, so I think I might kick off into the main workshop now. So thanks again for coming along. Again, sing out if anything comes up that you need, or get going in the voice channel up there. So yeah, we're going to be talking about MATLAB today. If you've started any engineering courses, you may have already been launched headfirst into it with your various workshops and stuff. If you want to throw up sort of any courses that you're doing that are using MATLAB at the moment in your you know, I imagine some of you are undergrad coming into it for the first time. Maybe there's a few who've had a bit more experience, but it'd be good to know what we're doing. Yes, civil engineering masters, awesome. So yeah, MATLAB stands for Matrix Laboratory. And yeah, it's really a mathematically centered programming language and programming environment. So if you've got any sort of mathematical problem to solve, MATLAB is usually a really good first stop for solving that and doing it. Some of the downsides of MATLAB are it's pretty expensive. It's proprietary software, and they to get an actual non-student license, like a commercial license, is quite expensive. The sort of model that MATLAB and MathWorks, who's the company that produces MATLAB, has taken is to get into the students while they're at university. So they partner with universities, give them student licenses. Everyone loves using it because it's a really great tool, but they get you when you're studying. You take that onto your professional life and you go, what do I need to solve this? I need MATLAB. And then your company needs to buy licenses, and that's how they earn a lot of their money. So luckily for us as students, yeah, we can usually get a student license, and as Cody's just mentioned, yeah, there's Octave as well, which pretty much clones MATLAB in a lot of ways, but in some ways is sort of falls short a bit. So if you do have any, MATLAB uses that you don't really need the whole MATLAB for, Octave is a good way to go. As we go through, any pages in the slide with orange are going to be problems for you guys to solve. And yeah, there's a few of those. So as I said, it's basically used for anywhere you want to solve a mathematical problem first and foremost. So thermodynamics, mechanical designs, fluid dynamics, any sorts of dynamics, control, lots of different stuff. You probably won't find too many like websites coded in MATLAB or like back-end systems coded in MATLAB. It's just not that sort of programming tool. I'm sure it can be done, but it's not the best tool for the job. So yeah, always know what you want to use a particular programming language for. There's lots of pros and cons with each. And yeah, maths and MATLAB are hand in hand. And I'll just mention, sorry, my camera's here, my second big screen's over here, so if it looks like I'm giving you the side eye, it's because I'm looking at my other screen over here. So if we fire up MATLAB, we're going to see three main places on there, and I'll just switch over to my main window here. We've got the main command window, we've got a workspace, what else did they give us? The editor. So if I don't have the editor up at the moment, you may not have the editor come up when you first open MATLAB, but to get that up we need to create a new script or a new file. So under new, script should bring up the inbuilt editor to give you a blank script in there, and that'll sort of mirror what that slide says there. So the editor, the command window, and the workspace over here. Depending on how much programming knowledge you have, we're going to have a little bit of assumed knowledge in terms of programming. Only a tiny bit though, so if anything is confusing, just sing out and let me know. We're going to work with something called variables, and variables store a value of something, and they store it in our workspace. So in MATLAB, variables must start with a letter. Can only contain alphanumeric characters, and you can't use any special characters in that. The way we initialize a variable, if we just go down to our command window down here, I can say I'm going to call my variable A. Go A equals, I'm going to set my variable A equal to the value of 1. So A equals 1, I type that in, press enter, and that's going to give us a variable A in our workspace over here. And then if I want to see what value is stored in that, I can just go to my command window, type in A, press enter, and it basically stores that variable in there. So anyone want to have a go at telling me what variable names are going to be valid and invalid out of this list? Sing out or throw it in the text chat. Should be pretty clear, so I think this one should be okay. This one probably not okay. This one should be okay. Can't start with a number, so that one won't be okay. And this one I don't remember with dashes. We can test some of these out. My variable 1, 2, 3 equals, let's set that to the number 5 or something like that. Yep, that's okay. What happens if I start it with 1, 2, 3? My variable equals 1. So we've got an error here. So always read your big red error messages whenever you're programming. Error, incorrect use of equals operator. Because I've typed that in wrong. Get rid of that. Here we go, invalid expression. So check for missing multiplication operator or something. We can see sort of where we're going wrong here. So we're starting with something that's just not right. So just you want to make sure you name your variables correctly when you're doing it. At its sort of simplest uses, MATLAB can be used as a big scientific calculator or a big calculator, so we can do basic mathematical commands, but we can also use variables in here. So maybe try some of these You can see what sort of stuff it's going to get here. So 2 times 2 will give you 4, hopefully. If we store something in the variable a, multiply it by 2, we can get the various different answers coming out here. So you can use not just numbers that you type in, but values that are stored in variables. And you can have a look at our workspace as we go through this. We can see what variables get stored over in the right-hand side of our workspace. We can see what we have access to when we're doing different things. And you know, if you try and access a variable that's not in your workspace, we can see what's come up. So in my workspace, I don't have any variable called like C at the moment. So if I try and see what's in C, unrecognized function or variable there. So pretty straightforward error messages coming up, which can be handy. Some useful commands here. So the variables that are stored in the workspace are temporary. If we close down MATLAB and then open it up again tomorrow, our workspace will be clear. There won't be anything in there. So if we want to save those for later use, we can use the save command, and that's going to save any variables that are in our workspace into a file. So if I just do save, it's going to save to, it tells me where I save everything to. And then basically if I want to load that up, I can follow the instructions here. So loading different things. If I go save vars, that saved it to a vars .mat file. So on the left hand side, it can show you in the current folder what different things you have in there. So the working folder structure of MATLAB can be a little bit tricky sometimes, but basically you want to make sure that you navigate to, using this top bar, to the path on your computer where you're doing your work. And that way MATLAB knows which files it has immediate access to. And all the files and stuff will show up in this, this left-hand pane. And so I can load up, can clear all my variables out of my workspace. So if I have nothing in my workspace now, and I say load vars, it's looked at my current folder, it's looked for a file called vars.mat, and it's loaded the variables that were stored in that folder back into my workspace. So now I have access to those again, which is very handy if you want to save your work and come back to it tomorrow. Scripts are another way to do that, and we'll talk about those in a second, but save and load. And always be aware of what variables are in your workspace, because you can sort of run into a few troubles sometimes if you have unexpected things in there, or there's something that you're missing from your workspace. So to see what is in your workspace, you can use who and whose. They'll list your current variables and give a detailed list of what current variables are in your workspace there, which can be handy. But often looking at the workspace pane is sufficient. I rarely will use who or whose unless I need to figure out what's in there programmatically, but oftentimes you won't need to do that. The semicolon. So if you've done any programming in other languages, semicolons are pretty ubiquitous a lot. For MATLAB, they have a slightly different usage. You don't have to use them, but they're called a suppression operator. Let's have a look. If I quickly say a variable, let's look what the difference is. Let's say a equals 1 with no semicolon. I get a equals 1 sort of printed out after I hit enter there. If I do that again, but I include the semicolon this time, so a equals 1 and then a semicolon, it works slightly differently. You notice that it doesn't print out anything afterwards. So if you don't include semicolons when you're sort of typing things into a script or something, often you get a lot of stuff just coming out into your command window as things are getting run. But if you include the semicolon, it can keep things nice and sort of nice and suppressed, and you don't need to see all the output unless you want to, of course, which can be super handy. Instead of typing in directly to the command line each time like a calculator, programming we like to use bits of reusable code like scripts. They can run other scripts and other functions from within themselves. And it prevents you from needing to sort of type in each line individually. We can have sort of a programmatical way to step through different steps. Yeah, I'll just mention, Thomas, if you don't mind just muting yourself if you're not talking, just to keep the voice channel quiet, that'd be much appreciated. So we're going to have a look at creating some scripts. Or do we in the thing? Not really, but we might explore some of this stuff in a script. So let's set up some variables. Let's say a equals 1. And this is, if you didn't see before, this is in a new untitled script created by clicking on the new button and then a script, or Control N, Command N on a Mac by the looks of it. And that should bring up a blank script in the editor. So I'm going to say a equals 1, next line b equals 5, maybe c equals 4, something like that in my script. And to run a script, we click on the big Run button up here, which is under the Editor tab. You'll get a message probably saying that you need to save your work. So I'm going to just save my script as MATLAB Workshop Sem 2. What are we? Yeah, Semester 2. And save that in your working folder that you want to save it into. So see the names change there, and then I'll just clear out my variables. And if I run this script now, you can see over in my workspace I've now got those 3 variables that I defined in my script showing up in my workspace now, and they would be accessible from my command window if I need to. I can see what value is in A or B or C as needed. So scripts are basically where you want to do most of your MATLAB work. You don't want to be typing everything into the command window every single time you need to do it. So yeah, first order of business, start a new script for that. Okay, so conditionals. These are a way to compare values to one another. If you've done any sort of maths before, this should be pretty straightforward. So we've got a less than, it will check if A is less than B, less than or equal to, greater than or equal to, all pretty straightforward. To use equals, like exactly equals to something, we need to use 2 equal signs in a row, which is pretty common across all programming languages. Because if we just use 1 equals, that's the same as assigning a variable like I've done here. So if you need to compare 2 numbers, use 2 equals like this, or not equals is like this, the tilde equals or squiggly equals colloquially. So they all return a value known as in MATLAB as a logical. If something is true, it will be logical 1. If something is false, it will be logical 0. So let's just try that in my script. If I want to see is A less than B. And then maybe I want to do is B equal to C. Now if I run my script, notice I haven't included semicolons after here. So it's going to output something to my command window. The first thing that comes up is the first line as it steps through sequentially. So line 5 I've said is A less than B. A is 1, B is 5. So A indeed should be less than B. And the first output I get is a logical 1. So that's a logical true. So yes, that's correct. A is less than B. And is B equal to C? Is 5 equal to 4? No, it's not. So I get a logical 0 down in there. And that should be relatively familiar, straightforward, pretty standard programming stuff, and mathematical stuff as well, less conditionals. we usually use conditionals for making decisions. We can see a sort of decision-making flow here. If a condition is true, we want to do something, or if a condition is false, we might want to do something else, or just move on to the rest of the code completely. And in MATLAB, we use ifs. So in code, it looks like this. If, and we always, on the start of in a conditional, we always want to be comparing to a conditional or logical statement. So if C is less than 50, we want to do something. This display function does sort of, or disp is short for display. It does pretty much what you'd expect. For example, if I do disp C down here, you can see I've still got my outputs from my logical statements that I did, and then there's my disp C here, displaying 4 for C there. So disp will just output something to the console, to the command window. So that can be super handy if you need it. So this is some quick decision-making stuff. I'm not going to spend too much time on this because I want to get to the more interesting things. But if you haven't done this sort of stuff before, this is the real building blocks and basics of writing any sort of code, and particularly MATLAB code. So ifs. So this block in here will only display the value of A if C is less than 50. If C is not less than 50, we're going to just go down to this part here. So this is this control flow here in terms of this these block diagrams, and this is what the code looks like. Can do similar things with a if-else structure. So if something is true, do something. If that is false, we're going to do something else, and then we're going to move on to the rest of the code. And in code, that looks like this. If C is less than 50, we're going to do display A, so that's coming down this branch here, and then we wouldn't do anything in this else block if we did come down this branch. We go straight on to the display C part of it. So if this part is true, we skip the else part and go straight down to the bottom here. But if this happened to be false, then we do go into this this branch here, and we do this display B part, and then we move on to the rest of the code there. So hopefully, if else's will be very handy there. And then we've got else ifs as well, which add another slightly modified control flow to our conditionals. So follow the branching here. If a condition is true, we do something and then we go move on. If something is false, and then we can check another condition. If that next thing is true, then we do something. Or if all of those are false, then we do the else and then we move on. And here's an example of that here with if, else if, and else's here. So I recommend that you type this code in yourself. If you're following along, you can hopefully type this in now. As I said, I'm sort of going to go relatively quickly and spend more time on the examples because there's a lot of content, but this is really good building block sort of stuff if you haven't done anything like this before. So we can use ors and ands in there as well to compare more than one thing at a time in those conditionals. So ors are with this vertical bar, and ands are with the ampersand structure. So that's like logical comparisons. So this whole conditional would return true if B is less than 4 or C is greater than D, whatever values are stored in B, C, and D there. So hopefully ors and ands you're somewhat familiar with. If B is less than 4 and C is greater than D, then this whole statement would be true. If one of these was false, say if C was not greater than D, then this whole statement would be false because of the and there. They both need to be true for the and. For the or, only one of these two things needs to be true for that whole thing to be true. So relatively Sort of linked to English descriptions of ands and or if you haven't come across it before. Should be, sort of tweak some language sort of stuff for you, but if you haven't, maybe refresh on some formal Boolean logic to refresh there. Display, so disp we've come across before. It's going to just display the things between the bracket with no special formatting. We do have format short and format long. I'll show you about that in a second. Printf is sort of for more control over exactly what gets printed out to the command line. You don't need it all the time, but it can be handy if display is not quite doing what you want it to do. So I'll just show you an example of format short and format long. Let's clear all my variables in CLC. Pi, as with any good programmatical mathematical language, pi is a variable that we have access to straight away just by typing pi. And we can see 3.146 coming up in our display here. If I type format long and then type pi again, I get a longer decimal representation of pi coming out to my command console. Now note, it doesn't actually change what value is used for the actual computations that you're doing with that number. It's just for display purposes, and I can change that back to format short. And then if I type pi again, it's going to go back to 3.146, just for display purposes. And yeah, sprintf is a slightly different way of going about that to display different types of values there. I think there's a example here. They use what's called format strings, which is this funny looking thing like %d and %f here. Oops, come back. %d and %f there in the format string. So if we use sprintf like this, it's going to print out to the command line this value, this string here. This is an integer 2, and we're using the %d formatter for that value to be, if we have a look up here, decimal notation signed, and this is a float %f. We have a look at this reference here, fixed point notation. So those two things can, sort of vary how numbers are presented when you're looking at them. So, all right, so we're going to go on to an example here. Hopefully, we've got some aspiring accountants in our midst. I know engineering can be pretty boring sometime, and we'd all love to live the sweet life of an accountant. So we're going to practice calculating income tax as per this example here. And this is going to help us get a handle on control flow using ifs, elses, and displays, and to calculate how much tax we owe based on whatever income we're making. So we've got a little sort of bare bones block for the sort of structure that we should be using here. So if you've got these slides, or I'll leave this one up for a second, the best way to start with this example will be to copy out the bare bones structure that is given here, and then we'll work on filling it in. If you're feeling brave, just jump on right ahead, see if you can get a solution. I might ask for any solutions that you come up with. If you're brave enough to post them up, we can have a look. Otherwise, I'll work through and show you my solution for this one as well. But I'll give a couple of seconds there to get your head around it. And yeah, jump into MATLAB, get some programming going along, do it in a script, call it tax or something like that, or just work with something, and we're going to figure out how to use our control flow to solve this problem. Just going to check my recording's still going. You will pay. So the MATLAB editor also highlights things really handily. You can sort of tell where any errors are sort of at a glance. So strings are included in these single quotes, and they will come up purple. And variables will just stay as black. Any comments, which are, I should have mentioned before, are done with the % sign. They will come up as green. So you say this, calculate income tax. Okay, so it's green there, and that doesn't get run by by MATLAB when you run your code. It's just there for human readable purposes. Okay, so if something and then disp something, just copying out the structure that they've given. And you always want to finish off, well, you have to, your blocks with end in there, otherwise they won't work. And you can see MATLAB's screaming at me at the moment with a lot of red little squiggles. And across on the right-hand side of your editor, if things are wrong, it's going to come up as bright red. And basically, it's because my if and else ifs don't have any conditionals that I'm checking there, just because we haven't written them yet. But this is the bare bones structure, so always keep an eye on the red squiggles and the right-hand side of your editor. It should give you hints about what's wrong there. All right. Okay, so how are we going to solve this one? What should go on our first if block? Anyone want to volunteer an answer? What's the first thing that we should check to solve this problem? And what's the calculation that we should do, if any? Anyone care to offer their solution? No worries. Hopefully you've all had a crack, because that's the only way to learn this programming stuff, is to write code, write good code, write bad code, write any code. Just have a try. So first thing that we should probably check as we step through our tax brackets. First easy one, what happens if our income is between 0 and $18,200? How much tax do we pay? 0. So that's probably the first thing that we should check. Is our income, which is stored in the variable called income, is it less than $18,200? Perhaps is it less than or equal to? So if income less than or equal to 18,200. Okay, so here's our conditional. Here's what I'm checking. I'm checking if the value stored in the income, this time it's set to $50,000, 500,000, not that rich, 50,000. If my income is set to $50,000, if my income is less than 18,200, how much tax do we pay and what do we want to display? Let's check our tax brackets. $0. We don't pay any tax if our income is within that bracket. Something like that, display $0. Else if, what's the next thing that we should check?
I just unmuted to answer,
Yep.
is that okay?
Yeah, of course.
But, yeah, just the next bracket, so between 18,201 and then for less than or equal to income, less than or equal to 37,000?
Yep. Yeah, so I could do two things. If I could do sort of check both sides of that bracket. I could do so if income, well, to be in that bracket, I'd need to be greater than 18,201, or greater than and equal to in this case, 18,201. And I should include that first thing in brackets. So if I'm greater than this value and income is less than or equal to, what was it? 37,000. 37,000. How much tax do I pay? 19 cents for each $1 over 18,200 there. So how would I do this part of the calculation to display the right amount of tax that I need to pay? Any clues for that one? Because there's a bit of calculation here. I don't have immediate access to the amount of tax that I need to pay. I need to do a bit of calculation there. So let's have a think. Logically, I need to pay 19 cents for each $1 over 18,200. So I'm going to do it in steps here. I'm going to call a new variable called something like dollars over. What's the amount of dollars over 18,200? So if my income, and then I'm just going to take away 18,200, right? So it's just a little bit of maths. So if I get my income and I take away 18,200, that's going to give me the amount of dollars over 18,200 that I need to do. And then, how much tax do I pay? I need to pay 19 cents for that amount. So the tax then could be calculated by something like tax equals 0.19 multiplied by dollars over. That's where I've stored how much dollars over. And then to display that, I can just put in tax there if I want to use the display statement like that. And that's going to display how many dollars. Slightly different from this one. You know, I could have included a 0 here and it's going to display 0 there. Depends on how you want to do it. So this is probably a little bit wordy. You can probably combine all these steps into one sort of one statement if you want to, but often laying it out step by step can help you work through, work through logically what's happening here. And once we've got this one, it should be relatively easy to expand to the next sets of tax brackets in the same way. So a few more else ifs for each of these tax brackets, and then same method for calculating the things, except instead of a set 19 cents for each dollars, for these ones we've got another fixed amount that we need to do include for that one there. So I'm not going to type all that out. I think hopefully that should be pretty straightforward. What I will do is share a solution. I definitely recommend trying it yourself if you haven't been able to do it and seeing how it works. So here's a full solution that I prepared earlier. It's doubled up my line breaks for some reason, but you get the idea. Similar sort of things. We can see comparing tax brackets, dollars over, the amount of tax. Here's where we include fixed amounts. Okay. And then if we wanted to actually use this, if we're an accountant, had a really dodgy accounting business that had a script to calculate all your tax, we'd say, okay, how much did you earn this year? They'd say $35,612. We'd run our script, and then we'd say, based on your income, you will pay 3.3 by 10 to the $3. Not formatted very nicely, so instead of disp, we might want to think about using our Printf statement here, but if we, should be 1, 2, 3, so that's $3,308.30. Can we see any shortcuts to simplify maybe these else-if brackets instead of comparing two values? Because if we do it in a logical order, we can just work through each tax bracket one at a time and only reference and only compare the upper bound on that. Because remember, it's going to step through each one in order. So our income, are we less than this amount? If we aren't, we're just going to go to the next one. So if we're not less than that amount, we don't really need to see if we're greater than that amount as well, because we know we definitely are greater than that amount because we've come through this if bracket, this if conditional. So we only would really need to compare the top bracket, something like that, and we just step through one at a time. But the advantage of including explicit references to each of the tax brackets, it can be a little bit easier for humans to read, or I could put out of order the different brackets or change the brackets later, and we can be sure it's going to work sort of correctly there. So there's no right or wrong way. There's so many different ways to solve each individual programming problem, but should be aware that there's definitely different ways to go about things, and if it solves the problem, then generally it's a good way. Okay, let's keep going pretty quick now. Really want to get to the fun stuff. Loops. Loops will rerun sections of code without you having to copy and paste a bunch of times. There's two main examples of loops. There's while loops and there's for loops, which we'll see. So this is a while loop, and a while loop compares basically checks a conditional. So that here's the conditional, while I is less than 5. Remember, that's going to return either a logical 1 or a logical 0, true or false. And the while loop will just keep running. It'll run through line by line, go back to the top all the time that this conditional is true. If that becomes false, then it will stop and move on to the next part of your code. So what is the value of I at the end of this loop? Anyone want to yell out an answer? Any ideas? Otherwise, I'll step through. One by one, we can become little versions of MATLAB without even typing any code. So what is the value of I at the end of this loop? So imagine where MATLAB we're going through, we see I equals 0. Okay, so we keep that in our heads. I is 0 at the moment, while I is less than 5. So is I less than 5? I is 0, so is 0 less than 5? Yes, it is. So we're going to run our loop code. Display I. So that's 0, so we're going to see print out 0, and we're going to say I equals I plus 1. So 0 plus 1 is 1, and we're going to store that to the value I. So I is now 1. And we go back to the top of our loop code. While I, which is now 1, is less than 5, I'm going to run my loop code. Yes, 1 is less than 5. I'm going to display I, which is 1. And now I add 1 to I again, so it's now 2. So you can see every time this loop code runs, I is going to go up by 1. So each time we increase. So when is the first time that this is going to be false and we stop looping? Well, that's when I becomes 5. So 5 is not less than 5. 5 is, it's less than and equal to 5, but it's not less than 5. So the value for I should be 5 on the last one of those. And then we don't need to run it anymore. And we just move on to the rest of our code. Fors are similar, except usually we use them when we know exactly how many iterations or how many loops we want to do each time. And we see here this code has the same functionality. It just looks a little bit cleaner. For I equals 0 to 5. So we'll see a little bit later on, this is creating a vector. In fact, I'll demonstrate. I'll just clear that out. So if I say 0 and then :5, it's going to create what's called a vector, which is basically a list of different numbers. And MATLAB knows it turns this statement into this list of numbers. So 0, 1, 2, 3, 4, 5. So this is a shorthand way of defining all these numbers. And what's happening here is for every time we loop the code, it's going to loop over each one of these numbers that it comes across. So for I equals 0 to 5, the first one is 0, it's going to display 0. The next one is 1, display 1, 2, 3, 4, 5, and so on. So type that in if you need to into your own MATLAB. And here we go, here's the semicolon operator. Creates a row vector of evenly spaced elements. We can extend it with this idea of a start, a step size, and then an end. Sort of the default step size is 1, it'll go through one at a time. But we can include a step size of say 2 here to step through, count up in 2s basically. So start is 0, step size is 2, and my end value is 10. And that will give 0, 2, 4, 6, 8, 10. Question, how do we create a row vector that starts at 30, counts backwards to 0 in steps of 5? See if you can figure that one out. So think about start, stop, and step. Throw it up in the text chat if you want, or yell it out. We'll see if anyone can come up with the answer. Starting at 30, count backwards to 0 in steps of 5. Okay, start value 30. Step value. For this one, what's our step going to be? We don't want to count forwards, we want to count backwards in steps of 5. So counting forwards in steps of 5, we might do 5, but counting backwards, -5. And then stop value is 0. Let's see what that comes up with. Here we go, 30, 25, 20, 15, 10, 5, 0. Starting at 30, counting backwards in steps of 5 until we get to 0. Perfect. So 30 minus 5 and 0, we can use minus in our step size to go backwards, which is handy sometimes. Breaks and continues. Sometimes we don't want to always go through every single loop. Sometimes we want to finish early, or sometimes we want to skip a particular loop. That can be done using break or continue. So investigate what breaks and continues can do. You'll sort of know when you want to use them as the problems arise. It's sort of like, oh, why would I want to do that at the moment? But when you're solving a problem, you'll often figure out, oh, I need to stop now, or I need to skip this one for some reason. So breaks and continues should be in your arsenal. Okay, so here's a nice example for you that I'll give you a bit of time on. And we're just about to come up on about an hour. So I usually have a bit of a break at the hour mark, which I might do this time. And give you a bit of time to solve this problem as well, or have a try at solving this problem. Yeah, we want to write some code to find, determine whether n is a prime number. So given an integer n, determine whether n is a prime number. we've got a hint there that mod a comma b returns the remainder of a divided by b. So have a think how we can use that to find whether it's prime or not. And yeah, as I said, we'll have a 5 or so minute break and come back and discuss any solutions that you've got, or come up with any problems that you've had so far, and then we'll launch into the second half of the workshop. So feel free to take 5, and I'll be back soon. Thanks so much for joining us, and yeah, hopefully you'll stick around for the second half. Alrighty, welcome back. Thanks for sticking around, Amelia. If you're there, if you managed to have a break, good on you. Good.
Oh no, I suck at MATLAB, so I'm just trying, but not getting anywhere.
No worries. Any particular issues so far? Or sort of in general?
Just in general, I'm going back to basics.
Yep.
So I just thought I'd come on and like try and refresh, but I was never great at MATLAB, so it's like learning it from the start.
Yep. Yeah, no worries. It's sort of that programmatical algorithmic way of thinking, and learning the sort of building blocks. Like ideally I'd spend, a fair bit of time on those early building blocks and just that sort of way of thinking, but there's so much stuff that is sort of essential knowledge. It's sort of, we got to move a little bit quickly. So we'll be going through. If there isn't anything that's like particularly confusing, feel free to hold me up, and we can talk about it some more. Whether we get anyone else coming back in the second half, we'll see. I mean, I got to run the whole workshop anyway because I've had a bunch of requests for recordings and whatnot. So I'll be presenting to no one if you're not here. So, yeah, happy to spend any extra time on things if there's particular problems coming up. And yeah, doing examples like this is the sort of best way to solve problems and stimulate that way of thinking. So, any ideas for solving this prime finder one? Did you get anything up?
No, I wrote something really dumb, and I know it's dumb.
That's all right. 99% of the code that I write is dumb.
Yeah, it started with the for statement, setting like I equals 1, like with the colon to 11. And then I started doing an if statement, using that mod function with and I, and then cycling through dividing, like seeing if the mod and I equals. I don't know. I really don't know what I was trying to do.
Yeah, no, it absolutely sounds like you're on exactly the right track there. It's just there's two things with programming like this. One is solving the idea in your head and getting what you want to solve in your head sort of clear, and then there's the completely separate problem of writing the code to solve that problem. So using the tools that we've got, and you're on the right track here. We're going to start, and well, first of all, what defines a prime number? It's a number that can only be one in itself, right?
Yeah, that's what I was trying to get at.
Yeah, perfect. So that's at the core of the problem. What tools have we been given to figure it out? It's this mod function, right? And it returns the remainder. So how do we use the output of this mod function to figure out whether a number is prime? Let's just have a play around with that mod function. Mod, let's say, so our number is 11 that we're sort of working with to start with. So, if we wanted to check, say, is 11 divisible by 4? The answer 3 is coming out here. Why is that? It's because if 4 is our divisor, well, we get 4 and then 8 and then a remainder of 3 gets us up to 11 there, right? Is what that's doing. So if, say, 10, if we're dealing with the number 10 instead of 11, mod 10 2 is going to be 0 because 2 goes into 10 and 5 goes into 10 as well. So what outputs do we expect for a prime number if we wanted to check every single one? So if we check if it's divided by 2, we get a remainder of something that isn't 0. If we check it 3, we're going to get another remainder that isn't 0. 4, a number that isn't 0. And that's sort of the track that you're on, right? We're going to count up from all the numbers starting from the bottom, go all the way up to the number that we're checking, and we check every single divisor and see if any of those come out to be 0. Because if one does come out to be 0, all of a sudden we know that the number isn't prime anymore. So that's what I think is the first step in solving any problem like this, is talking through the problem. Out loud or common in programming is something called rubber duck debugging, where you get a little yellow rubber ducky sitting on your desk, and whenever you come up with a problem, you pick it up, you look at it, and you go, here's my problems, here's what I think is wrong, and you talk to your rubber duck, and talking it out loud will often solve the problem. So yeah, rubber ducky debugging, very handy. But that's essentially what we want to do. So let's start out with the boilerplate that they had. So n equals 11, and we've got a for loop, that's it. So n equals 11, and for something, and then end. Okay, so the idea that we came up with was counting up through every single number to our top number. So you had something sort of half written down for that. What was your actual statement for the for loop that you had?
So I had for I equals 1:11.
1:11. Yep. And did you type in the number 11?
Yeah.
Okay.
Just on n.
Let's use n in this case, because what happens if, every time we change the number that we want to check, we don't want to change it in multiple places. So if we go to n.
Yeah.
So do we want to start at the number 1? What is mod 11, 1? It's 0. So 11 is a prime number and it's divisible by 1. Every number is divisible by 1, right? So we don't necessarily want to start at 1 because we don't need to check 1. So instead of 1, let's start at 2 because that's the actual first interesting divisor that we need to start by checking. And what number should we count up to? Should we go all the way up to 11? Yeah, we want to stop at 10. So we absolutely can. You just want to make sure you include it in a bracket, because otherwise it will do something slightly different. For example, if I did 1 to 11 minus 1, you can see it's going 1 to 10, which actually, works, I think, but maybe if n was different. Anyway, best for readability to include it in a bracket like this, I find. So I, in this case, is taking the place of our divisor. And let's use our mod statement now. Remainder equals mod n, comma I, right? So hopefully you had something like that. Did you call it remainder?
I used an if statement and it literally counted through from 1 to 11 and said prime, not prime, not prime, not prime.
Ah, yep, okay.
It was silly, yeah.
Yep. No, that absolutely works. And this goes into something about like usability and readability of what the actual output of our code is. So if we had, for example, like if, so this is going to check the remainder. If the remainder is what we could say equals 0, and then we could display prime, but that doesn't particularly solve our problem. because, you know, we're only checking one at a time. Maybe we could do if remainder is not equal to 0, then we could say not prime, and then we could use our break statement, which we haven't done, because that will do every time it checks. As soon as it comes across any divisor, any remainder that's not 0, we know that it's not prime. Sorry. No, we do want to check any remainder that is 0. We know that it's not prime. So all the non-zero divisors indicate that it could be prime, but a 0 remainder definitely is not prime. So we could do something like this, and that will break out of the for loop there. So if I run this now, for 11 it never prints anything because it never goes into this if statement. If I say had 8 instead of 11, it does, because it finds 1. If I wanted to maybe give us a little bit more useful information, I could do display let's use instead of display, go back to disp, let's go E is divisible by, and then I would do n comma I, like this, and that might give us a little bit more useful information. Not prime. 8 is divisible by 2, so it's stopped at the very first number that it's found that divides 8. Now, depending on exactly what sort of information we want to provide to the user, we might think about different kinds of control flow, and, you know, print out whether it's prime or not prime at different ways. But I'd say at the heart of the issue, we've solved this problem, right? We just haven't, you know, polished it up for particular use sometimes. So yeah, I find talking through the problem first and then writing the code can be two very separate steps. Sometimes they get a little bit linked, but keeping it separate is a good idea too. So good, I think you definitely solved the problem and then just didn't quite get it implemented in code. Excellent. Okay, we'll talk quickly about vectors now. I won't spend too much on it. We've sort of come across vectors already in the in doing something like 1 to 10. This is actually, you know, the output of this is a vector, and it's a row vector. We get row and columns. This is math, so we like to think of row vectors, column vectors, matrices, things like that. So if we want to define one explicitly, we can use square brackets like this, and notice we separate them by spaces, or we can separate numbers by commas as well. They'll both define row vectors, but you only want to use one. Don't mix commas and spaces. We can do column vectors, which are elements are delimited by semicolons within the square brackets like this. And when we look at that variable, it will list the elements downwards like a column, so it's pretty straightforward. The single quote at the end of a vector is transpose, so it'll turn a row vector into a column vector or vice versa. So our usual transpose sort of operator in maths, matrices and things like that. We access elements of a vector by using round parentheses, round brackets, and the number that we put in the round brackets accesses the that number element. So if I was to say a equals 1 to 10, actually let's make it a little bit more interesting. Let's go minus 10 to 0. So there is my A vector. It's a row vector. if I want to access the first element, I do a round bracket 1, and that's going to give me back the value that's stored in the first element there. If I want to get the second element, so the -9 here, I would do the second one like that. Some programming languages are what's called 0 indexed. MATLAB is 1 indexed, so the first element is accessed by the number 1 there. Another handy one, if you want to know what the end or the last element is, you can use end. We'll give you what's at the end position. You can use like the second last, you go like end -1, give you the second last. You can also, and I think we talk about this, oopsies. So yeah, just make sure your index is within the bounds of your array. So my array A has 11 elements. We can see in my workspace here, A has 1 by 11, so there's 11 things in there. If I try and access, say, the 15th element, I get an error here. Index exceeds the number of array elements. Pretty straightforward, the error that it's giving you. So make sure that's always within the bounds. We can use access multiple elements by sort of giving it another subvector that defines the indexes or the indices that we want to access. If I want to access the first 5 elements, I would index it like this. So the elements of A from 1 to 5, and that's going to give me those first 5 elements back from that array. Like that. Addition and subtraction, so you can add together and subtract away. That works pretty much how you would expect for vectors. They're the same size. We can just add up the elements one by one, and that's going to give us the corresponding elements from that mathematical operation. See what happens if they contain different amounts of elements. You'll find that it doesn't quite work. Multiplying a vector by a scalar. You want to be very careful when you're using multiplication in MATLAB, because for better or for worse, they've made the symbol for scalar multiplication the same as the symbol for matrix multiplication. So if you want to, we're only dealing with vectors at the moment and scalars, so this will do what you expect. If we multiply the vector A by 5 and store it in the new variable E, it's going to multiply everything that was an A by 5 one at a time and give us what we expect. But if there was 2 matrices that we're multiplying together, we need to know whether we want to multiply each element individually or do an actual matrix multiplication, the rows and columns addition thing. So just be careful with the multiplication. We can do appending vectors, or concatenating is a technical term for joining 2 vectors together. And yeah, we can do those in different ways here, so feel free to refer back to this if you find you need to do that. Array element multiplication. So yeah, this is what I'm talking about. We can use this dot before operator, in this case multiply, to force MATLAB to do element-wise multiplication. So if I did h equals 1, 2, 3, 4, 5, so let's just follow this example here. H equals 1 to 5. So that if I did I equals h dot times h, what that does, it's going to take h, it's going to multiply each element by the corresponding element in the other matrix. In this case, it's itself. So it's going to do 1 times 1, then 2 times 2, 3 times 3, 4 times 4, and 5 times 5, and then store that into the variable I. So we expect I to have 5 elements, and we expect it to have the values of 1, 4, 9, 16, and 25. And there it is there, 1, 4, 9, 16, and 25. If I hadn't have included that dot, let's just see what happens. Error using multiply. Incorrect dimensions for matrix multiplication. So yeah, gives us an error there. If I had a square matrix, we'd be in trouble because it just would have gone ahead and done a matrix multiplication instead of element-wise multiplication. Let's have a look. We can see some inbuilt things like sums, square roots, so mathematical operations, depending on what we want to do. We can multiply two vectors, and like a row vector by a column vector. So this is doing the like the matrix multiplication version. You see there, if we've got a row and a column, it's giving us a single number out. You know, outer product, inner product type stuff, depending on whether we're using column by row or row by column. So yeah, just be sort of careful when you're using that multiply. Most of the time, you're going to want to be doing element-wise multiplication, so including the dot there, but you don't have to. Matrices, extensions of row and column vectors, some more math stuff. Pretty straightforward. Let's quickly show some indexing stuff. So we do indexing by round brackets again, except we can give it two numbers for a matrix by giving the row and then the column of what we want to do. Let's just create a quick 5 by 5 matrix here. So there's my A. It's got 5 rows and 5 columns. If I want to extract only the first row, I think I always get these mixed up. We can use the colon, which sort of in this context stands for all. So let's have a look at what that gives us. And that gives us the first column. So it's interpreted as give me all rows from the first column. And that's going to give us all of these rows from the first column. Similar, if I wanted the third column, I could go like this, 1576. That's, yeah, this one here. Same thing for, we could do give me the first row and all the columns like that. And it's going to give me rows from my square matrix or any size matrix or two-dimensional array. Matrices, two-dimensional arrays, sort of one and the same in this case. And arrays can have any number of you know, any number of dimensions, rows, columns, and then, you know, the third dimension going back or fourth dimensions or whatever. They're just data structures that hold values. Deleting, we set it to the empty vector, which is just two square brackets after each other. Operations still apply to matrices. Again, you'll probably want to reinforce this sort of knowledge by going back over the slides. We'll get to some more fun stuff that uses these things. It takes a while to get comfortable. We've got our usual matrix functions that MATLAB has, so things like determinants of matrices, inverses. It's got good ways to figure those out. But again, yeah, we need to make sure we're following the mathematical rules for can you find the determinant and can you find an inverse of square matrices and so on. Need to make sure we're following mathematical stuff as well. Have a try with some of these, see what happens. Zeros, ones, I, and rand. Just quickly type those in, see what comes up, see if it makes sense. Zeros is going to give us all zeros, dependent on the size that we've given it. Ones is going to give us ones, and this defines the size and the shape of the matrix that we want. Make sure to check on the workspace, see what's happening in your workspace when you do this. Assign it to a variable or something. I for identity and random for random numbers. And then we get a bunch of different functions that can help us to figure out things based on, you know, the size or how many elements are in them. We can sort the values in there. Yeah, things like that. Just be aware that they exist. You'll find their uses as they come up. Okay, do a little quick example of matrix manipulation and solving a problem. So let's solve the problem of a magic square. So magic squares are square matrices in which the sum of all elements along the row, column, and diagonal sum up to the same value. Magic squares also have all possible integers, 1 to 9 for a 3 by 3. Your job is to determine if a given matrix is magic, and there's a couple of test matrices there. It's a relatively big problem, this one. A lot of different things to check. But try and solve the problem, as I was saying to Amelia before, try and solve the problem out loud in your head. What steps do you want to take for your little algorithm to check? And then we can focus on writing code for that. So have a little think. I'll see if I can pull up my solution. It does take a little while. We'll probably discuss your general solutions that you come up with, maybe discuss some specifics of the code, and then we can have a look at my solution that I came up with there. So have a think, what's the first thing that we might want to check? What's the easiest thing to check maybe? And here's the, I'll post up in the text chat. Let's see if Discord does correct formatting. Yep. So there's the two matrices, the test matrices. There's the code that you can use to define those. So that's using what we learned earlier about how to define matrices by their rows and their columns. So you can use those and build from those. So the first thing that I did was check whether my rows were magic, and what's the check for whether rows are magic. It was they all the rows need to add up to the same value. So let's check this square matrix. 2 plus 7 is 9, plus 6 is 15. 9 plus 5 is 14, plus 1 is 15 again. 4 plus 3 is 7, plus 8 is 15. So indeed, for square matrix, all the rows are adding up to the same value. So we're looking good for magic on this one. What about this one? 2 plus 9 is 11, plus 6 is 17. And this one's 13, the second row is 13. So immediately we can tell that square matrix 2 is not a magic square, because the rows are suddenly adding up to different values. So that's just what I did manually. How can we recreate that in MATLAB? And once we've got that, the sort of checking of the columns should come quite naturally as well. We can use the same sort of idea for summing up down the rows. So the start of a solution, just getting a feel for summing up along rows. If I wanted to sum the first row, I could do sum of square matrix. I want to do the first row and all the columns like that. If I do that, that should give me, remember I added up manually, I got 15 before, and that's giving me 15 there. So that's the sum of all the first row If I want to do the second row, I'll do 2 there. And the third row there. Okay. And lo and behold, they're all coming out as 15 there. Instead, if I use the second matrix instead of the first one, just comment out that first line. All of a sudden there's my different values there, 17, 13, 15. So there's the start of a solution. And it's good golden rule in programming. If you find yourself copy and pasting, there's probably a better way to do things. Maybe using a loop. Here I'm looping over, what's this? This defines the number of rows that we had in a matrix. So maybe we want to programmatically find how many rows are in my matrix and then loop over them and do this sum and do some checking based on that. Anyone want to share anything from that? I've got a solution. It's a little bit probably different from how you might form your own solution with the knowledge that you have. Anyone want to walk me through some steps for what they might do to solve this magic matrix problem? All right, so generally it's just going through and checking each one of those conditions individually and then seeing if there's any failures to it, or if they all succeed, then we can be sure that it's a matrix, that it's a magic matrix. So I'm going to post up my solution, full solution in the chat. And there is a potential problem with this that I found out, so if you can spot the potential problem, please speak up and let me know. But we'll discuss it and check, sort of see, because there may be some things that we haven't seen there, but I'll just discuss what I have done. So at the top, we're defining those two matrices again. First thing I'm going to do is check the sums of the rows. We see a big, this is called nested functions. We've got a function inside another function, inside another function, inside another function. We can just break that down from the inside out. So if I wanted to check this, let's see what this very inner function is and what it looks like. Sum of square matrix and comma 2. So it might be a little bit different. We've got this other weird 2 hanging around there, but let's see what the output of that does. And this was, my square matrix was, I'll just rerun that, sorry. So sum of square matrix 2, what it's doing, it's summing up all of the rows and outputting them as a column. So 15 is the sum of the first row, 15 is the sum of the second row, 15 is the sum of the third row for that that very first square matrix here. So that's what the very inner part of that's doing. If you're unsure of what a function does, you can type help and then the function name. And then that gives you the documentation for usage of this function here. So the way that we're using it is sum of x along dim dimension. So dimension being whether we want to sum up all the rows or all the columns. That's what that one's doing there. So giving it the second dimension is going to sum up along all the columns and give us the sum of each row. So that's what that's doing. So now that we know what sum does, what does unique do? Well, we can check help unique, see what it does. So set unique. For the array A, returns the same values as in A but with no repetitions. So In this case, it's going to basically reduce it down to the unique elements of whatever array we give it. So in this case, we're giving it the output of the sum thing. So if I gave it all 15s, that's just going to give me back one number. It's going to give me back 115. So I can check that and just copy those two nested functions, paste that in. See, it's reduced those 3 lots of 15 down to just 1 because that's the one unique element in there. If I change that to square matrix 2, there was no double ups of numbers there, so all those numbers are unique, so it's going to be 3 there. What's this last thing doing? Num_L. Again, you can check the help. It tells you how many elements are in it. So if there's one element, like if there's only one number in there, it's going to give you back the number 1. If there's 2, it's going to give 2. If there's 3, 3, and so on. So how many elements are in it? So hopefully you might be able to see how this comparison, this big chained set of functions here, will tell me whether my rows are magic or not. So rows magic will be 1, a logical 1, if my rows are that of a magic square matrix. It will be a 0 if they're not. And yeah, just taking apart that chained set of functions can be a little bit involved, but really helpful. And then go through in your own time and figure out what each of these different what each of these different steps are doing. And I've got comments in there, and this last logical check should check whether it's sort of magic or not magic at the end. So quite involved. And yeah, if you do find out what the potential issue with this code is, let me know, because I'll be interested if anyone picks up on it. It's quite subtle, and I'm not sure whether it's mathematically possible or not. Yeah, if you can prove it one way or the other, that would be awesome. But yeah, there is a potential problem with this solution here, so just be aware. I'll just post it up for anyone coming along later.
Hey John, how's it going?
Good, thanks, Jeremy. How are you?
Tired.
Tired.
How's the workshop going?
We're going pretty well so far, I think, aren't we, guys? Hopefully. At least I'm having fun.
Yeah, learning heaps.
Oh, that's awesome.
Yeah.
Is it just like matrix manipulation and logics you're going through right now?
Yeah, so we're solving, there's a example problem for that they present for solution in the slides, which is finding out whether a given square matrix is a magic matrix. Yeah, so we've discussed general solutions, and I've posted up my example solutions. But yeah, I did note when I made this solution that there is a potential issue with it, but it's sort of subtle. So I'd be interested if anyone does come across it. But yeah, again, with this sort of stuff, guys, the only way to do it is to get your hands a bit dirty, come up with problems. Your first solution might look very, very rough and very, very long with lots of for loops and lots of ugliness. And yeah, writing code is always that balance against sort of economy of number of lines. You don't want to have a 1,000-line script that does something really simple. You want to hope a 1,000-line script is going to be sort of complicated and interesting. But in the same vein, you don't want something that solves your entire problem in one line, but it's so long and you can't read it. So it's always about striking that balance there. So yeah, in your own time, maybe have a good try at that magic squares example, and yeah, post up any solutions that you come across in the text chat for later review. But we'll keep going on. Talk about functions. We've seen functions so far, a lot of inbuilt functions. We can actually define our own, which is, we'll find some function syntax, scope. Have a read about scope here. We're sort of coming up. I know there's a lot of content to cover, so I'm not going to cover too much about function scopes here. The information is there to read and try. But essentially, we have used functions like sum is a function, numl, unique, rand, they're all the functions that we talked about before. We can create our own functions to do specific tasks. So the examples that they give come up with a function for finding the minimum out of a set of numbers. And I must say it's not the very best example of the way to find the minimum of a set of numbers that I've ever seen, but it serves the purpose of sort of, you know, explaining what functions do. MATLAB has a very good inbuilt min function to work on. So number properties, I don't think we'll do this one, but essentially functions are things that you want to reuse and use multiple times that solve one specific problem that you need to solve. And if you find yourself like copying and pasting code a lot, as we said, for loops or functions are a way to help you from just copying and pasting blocks of code a lot of the time. So functions you do need to write in a new file. So if you click on new, you'll see there's a few different templates you can work from. You can create a new function and see what comes up there. You've got this boilerplate used here to start you off on your function writing. Amelia, I'm not quite sure just yet where the recording will be uploaded to. It's going to depend on exactly how big it turns out to be and how much different delivery methods we can have. But yeah, stay tuned. Once I've processed this workshop, I'll be sure to mention where it ends up going, because yeah, not quite sure at the moment. So if we just stop on this mymin function for a second, you can see I've written this function here. It's in my MATLAB current folder, and I could use it. I could say mymin function. I need to give it 4 different numbers, 3, 7, 1, -2. And then if I call that function on those numbers, it does whatever processing it needs to do, however we've written it, to give you an answer back. In this case, it's giving us the smallest number out of this, which is -2, which indeed was the smallest out of those numbers that I gave it. So yeah, if you can think, if I don't want to be copying pasting this set of code all the time I want to use it, I can just write it in a function and then call that function whenever I do need to use it.
Yeah, as a general rule of thumb, if I could say something.
Of course.
If you find yourself writing the same block of code twice in your project, it's generally a good idea to write a function just for that code. So
yeah, exactly. DRY is what we say when we're programming. Dry. Don't repeat yourself. Copy pasting, not great. Slightly different form of a function is called an anonymous function, sometimes known as an inline function. We create them using the @ symbol here. You'll don't always need to create them, but they can be handy. They're sort of bordering on the advanced usage in a way. You don't need them all the time, but they can be handy to do something sort of quickly and off the cuff without creating a whole new file for each function. So for this one, I need a file called mymin function to create that function. If it was just a simple little thing that only you can do in one line, you might want to look at using an anonymous function like this, and an example here of how to use that. Plotting. Let's quickly have a try at some plotting, because this is mostly what you're going to be doing for presenting in reports and things like that. Example of a function here is linspace that we're using. That's going to create 100 equally spaced points between -100 and 100 as a vector, and then we're going to give that to the mypolynomial anonymous function that we created on the previous one. It's going to calculate that, store it in the value y, and then we're going to plot x versus y there. That's going to give us this sort of plot like this. So whenever you're plotting, you need an x value and a y value. It's going to create a line plot like this. And we can see here this polynomial. If we go back to what that my polynomial one was there, it was a quadratic that we defined as a polynomial. So there's our polynomial coming up there. Again, I want to keep motoring on. Styling the plots, hold on and hold off are useful. Okay, so let's show something. Let's bring up the example here. Just copy this over so I can explain it. Okay, so I've created a anonymous polynomial here. It's a quadratic, and I can run the where's it gone? So there's my plot of x versus y for this polynomial. X runs from -100 up to 100, and y gives me the value of the polynomial evaluated at all those points. This one here, let's have a look what happens with hold on and hold off. So first, I calculate the value of the polynomial, I create a second polynomial, which is slightly different than the first. This one is +1, this one's +1000, and then x and y in red. And then my polynomial 2, I call it y2, and then I'm going to plot x and y2 on the same set of axes here. So this is called a plot style, and it's going to do a red line. So R dash is going to create a red line in the plot styling. Come back plot. And we can see that red line here. So that's that first value coming up. And then I turn hold on. So hold on, what it does, it keeps the values in this plot, it keeps them on the plot, and then it plots whatever comes after it on that same set of axes. So if I didn't have hold on there, if I say commented that out, it's going to do something different. I'll show you that in a second, but I'll show you what this does first. So with hold on, I then plot x versus y2. In K for black and P for stars, obviously. There's some sort of reference somewhere about what each of these plot formatters do, and colors and the lines and the shapes and stuff. But KP obviously does black stars, because you can see my black stars coming up here for the values of x versus, y2 versus x. So this polynomial here versus x there. If I have hold off, let's see what happens. I only get the second thing that I plotted because this calling plot here overwrites the stuff that was in that plot and it's gone. So you want to use hold on if you want to plot multiple things at once. Yeah, so that can be pretty useful. There's some markers that we use for plots. Pluses, circles, dash lines, dotted lines, it's all there. Yeah, all on the MATLAB reference guide if you need to access it. Colors, extra things, so like labeling your axes, putting titles, all that good stuff for creating nice plots. All that sort of stuff is available. For example, if I turn the grid on, hopefully when I go back to my plot, yep, so now I've got a grid there. So grid on will turn the grid on, and you have all control over that sort of stuff, how fine the grid is, font, the colors, all that sort of stuff can be changed if you so desire. Subplots, it's sort of plotting two plots in the one figure. This will take you through an example of subplots, which I won't go through in detail, but you can do more than one plot on the same sort of axes if you need to present your data in that way. Surface plots, so 3D plots, can be used using mesh grid. We're going to create a parabolic surface with x squared plus y squared and store it into z, and then use surf of x, y, and z to create the surface. And hopefully we should get something like this. I probably won't do the subplot part. Let's just do the colorful part of the mesh here and defining that. Okay, so let's work through this one together. All right, so use the function meshGrid to create a 2D array of values. Store these variables into x and y and have our range from minus 0.2 to 0.2. So let's first have a look at what this meshGrid function does. So again, we'll use our help command at the command line, help meshGrid. And we'll just have a look at what's coming out there so we get an idea for what this meshGrid function does. Okay, Cartesian rectangular grid in 2D or 3D. So meshGrid of x and y returns a 2D grid coordinates based on the coordinates contained in vectors x and y. X is a matrix where each row is a copy of x, and y is a matrix where each column is a copy of y. The grid represented by the coordinates x and y has length y and rows and length x columns. Okay, so let's say I want x to run from, we said minus 0.2 to 0.2, and well, let's use linspace here probably. So linspace does start minus 0.2, 0.2, and it defaults to doing 100 different points there. Thanks, Jeremy. Catch you around. So linspace is going to do x from minus 0.2 to 0.2 and give us 100 different points. We'll do the same thing for y there as well. Okay, and we definitely want to suppress the output for this because we don't want 100 different numbers coming up. So I'll run that, we'll see what we're dealing with. We can see now I've got two different variables in my workspace, x and y. They've got 100 different values in them. There they all are. Starts at minus 0.2, runs all the way through to 0.2, and there's 100 different ones of them. So now I can use my meshGrid function. Usually we call them capitals, just by convention. meshGrid, and then x and y. It's going to fill in the 2D grid, we'll see in a second, in x and y when I run that. So I look in big X. You can see there's a lot of values in big X. Easiest to look up at your workspace and see. So big X has 100 by 100 now, and big Y has 100 by 100. And that's going to be useful when it comes time to plot our surface. So basically X and Y hold all the different individual points that we want to calculate Z at, because this is a 3D plot. And how does it want us to calculate Z? So Z, the height of it, is the value of X squared plus the value of Y squared. So it's a 2D parabola basically, and store it into Z. So equals, what should this one be? I'm going to do big X squared plus big Y squared. And then Z is now also 100 by 100. So for every single one of these X points and every single one of the corresponding Y points, it's taking the square of them and then adding them together. And then the result of that is going to store it in the value Z, which has 100 by 100. Okay, now we've done that, we've stored it into Z, and now we can use surf of X, Y, and Z. Let's just have a quick look at the help page for surf. So, surf of X, Y, Z plots the colored parametric surface defined by 4 matrix arguments. Viewpoint is defined by view. Probably this one. Yep, so surface height is what we're going to use here. And we can just try and see what happens if we do surf. We can do X, comma, Y, comma, Z. And see what happens. And there's our nice looking 3D surface here. And you should have controls for this plot, so we can rotate around this plot, see different things, look at it from different angles. Quite nice looking. You know, you've got things like zoom, you're zooming in and zooming out, sort of our usual plot controls here for manipulating these plots. So that can be quite nice. You can look at it from above. And yeah, we might have wanted to follow that with a semicolon so it didn't output a bunch of numbers for us. Sweet. Okay, and then yeah, this example asks us to create subplots. I'm not going to do the subplots for this one, just because yeah, we're running a little short on time. But this is what it would look like, and you can see there's our parabola. Same looking there. The scale's gone a bit different for ours though. If I wanted more points or less points, I can change how my base X and Y vectors are defined. So maybe I want only maybe 20 points running from -0.2 to 0.2. And that's going to give us a much coarser looking parabola now, like this. Okay. So you need to think about how each one of the different parameters that are going through into this final statement, the surface plot, are affecting, you know, if I did something really fine, so instead of 100, maybe I did 1,000. And then had a look at my plot. All of a sudden it doesn't look quite so good because my edges are black and there's just so little space for it. If I zoomed in, hopefully we might get some color coming up, or maybe not. Yep, too fine there. So 1,000, not a great value to choose there, but you can definitely play around with that to find exactly how much sort of resolution you might need in presenting that plot the way that you like. Excellent. Moving right along. Symbolic math. I honestly don't really like MATLAB for symbolic math. Yeah, exactly right. You want to make sure you choose the values carefully so you don't overload your laptop or something like that. Good, very good point. Very good point. Yeah, so I don't really like using MATLAB for symbolic math. Definitely prefer to do it by hand a little bit, and I find it's a little bit clunky as well, honestly, but it can be done. So symbolic math being, you know, if you wanted to solve simultaneous equations, you know, something can be done by hand, maybe you don't want to. You can do that using symbolic math. If anyone remembers or uses Wolfram Alpha at all, it certainly got me through my undergrad degree when most of Wolfram Alpha was free to give you the really detailed solutions of like integrals and derivatives and, you know, all those tricky things that you could never be bothered to do by hand. I think Wolfram's charging for a lot of that stuff now, unfortunately, for at least the detailed solutions. So yeah, MATLAB, if you've got it, might be a decent way to go, but I've never found it particularly intuitive or easy to do it this way. But it's all there. ODEs. So this is sort of a fun one that we can play with. This is the last example. So I'm doing okay for time, so we'll go through this and then I'll sort of answer any specific questions that we've got. But I find this one's fun. This creates a eventually, I think, builds on this. Actually creates a animation that will write to an MP4 file to your computer, which is quite fun. So builds off this using the ODE45 to solve a dynamic system. You can read up again if you want to figure out, oh, what's this function ODE45 doing? You know, jump back into your command line, type help ODE45, and that's going to give us some detailed documentation on exactly what that function is doing. But it's just essentially it solves a coupled system of differential equations between the values of t0 and t final, and here's the function sort of parameters that it requires here. Y0 is the initial values. Yep, we saw that in the help. Okay, so let's follow this through line by line and get some animations going. We'll probably spend like 15 minutes. Try and get this one happening on your computers as well. It's quite fun and satisfying to have coming out, like actually creating a little video. Can be, yeah, it's a nice feeling. So just follow this line by line. I think it lays out the whole solution here, which is pretty handy. I'll go through it and we'll talk about any particular lines that look a bit you know, confusing maybe. But yeah, we'll work through here. So create a file with the name myanimationvideo.avi, set the frame rate, and then open the video file there. So just copying these out word for word. We'll just take it by rote, and here's sort of the final code here. So we'll reference this one and talk about each line. So frame rate dt is 0.01. Frame rate is 1 on dt obviously, and then we're opening up the video file. So hopefully you've got the reference on your end. So to type this in, just to make sure I'm working through it roughly the same speed that you are, I'll type it out by hand. dt equals 0.01. Video file equals. Oop. Okay, so this is creating a video file. It's creating a video writer object. It's called in this video file variable. So we can access certain things about the video writer and utilize its functionality by accessing the video file variable. We're going to set the frame rate. One on dt, and then see if I run this now. We'll see just what appears in our workspace. We've got dt as a variable, obviously, as we expect, and we've got this video file object as well, which is a value as a video writer object, and we can see what's going on with that one by typing it in, pressing enter, and it comes up with all this different parameters and properties of this video writer thing that we're defining as we go. All right, next one, open video file. So that is going to open, it's called a file stream. You don't really need to worry about exactly what it is, but it opens a file stream based on the file name that we've created here in the path that it's going to. So open video file. What's next? F equals. So this is an anonymous function, and it's creating an anonymous function specifically for use with the ODE45 function that we want. So this defines the coupled set of differential equations for this particular problem, and that's this dynamical system here. So the derivative of x1 equals 3 times the value of x1 minus 13 times the value of x2. And the derivative of x2 equals 5 times the value of x1 plus the value of x2. And this function handle here, f, defines these two systems. Hopefully you can sort of see, based on the numbers that are involved, how it's set out in terms of rows and columns, how this relates to this mathematical definition here. So 3 times the value of x1 minus 13 times the value of x2. That's what that's doing there. And on the next row, we've got 5 times the value of x1 plus the value of x2. So that's exactly this mathematical equation here, encapsulated in this function, anonymous function here. So we'll quickly get that in there. Okay, x equals 3 by x1 minus 13 by x2, x1 divided by x1 plus the value of x2. So that is accessing the elements of this capital X. So element number 1, element number 2, element number 1, element number 2. Okay. Set some more things. Initial value equals 0, 12. And then time span equals, I'm going to solve it from time 0 to time 1.5. And t, comma a, oops, can't type, getting late, haven't had dinner. Ta equals ODE 45, f, our system of equations here, between time span with initial values y0. So that, if I run this code now, what's wrong here? What have I done? Dimensions of arrays being concatenated are not consistent. Why not? What have I done wrong? Yeah, it must be getting late. Maybe that. Yeah, that I think. Yep, that worked better. So I just had my vector defined wrong. Use a space, not a comma. Okay, so now I should get values in the output from this ODE45 function, t and a. Let's have a look. T gives me time values all the way from 0 up until my final value 1.5, just like we asked for. And what's in the variable a? It is all the values of x1 and x2. So the system that we asked it to solve, it's all those values at each individual time step. And note where it starts. What's the first one? 0 for x1 and 12 for x2. And there's our initial condition, 0 for x1, 12 for x2. And then basically ODE45 says, given how my system evolves, go through and show me how those two variables change from the start to the finish. So that's what it's done. Okay, next up, we need to plot it. So plotting all the values of A, all the rows from the first column and all the rows from the second column. So we'll chuck that in and see what comes up. figure creates a new figure. Hold on, we saw about that before. And plot all rows, first column, and all rows, second column. All right, let's see what that looks like. And I get this lovely looking spiral coming up, which is nice. Basically, all the values of the very first point that comes up is 0, 12. So there's our first one. If I show what the next value is, where's my figure gone? If I could get in there closely to show you what the next point is, it should come up in that list somewhere in there. So remember, there's a fair few values there. So next, for the animation, we use a for loop, and essentially what it's doing for the animation is it's going to plot a red dot at the value. So say this first value is going to put a red dot, and then it's going to save the video frame. And if you know about videos, they're just a sequence of different frames all stitched together, and play them quick enough and it looks like a nice smooth animation. So that's what we're doing. We're plotting a red dot, saving the frame, moving the red dot, saving the frame, plotting a red dot, saving a frame, and so on. And that's what this for loop's doing. We wouldn't want to write every single frame of this video individually. That'd take too long. So use the for loop. Equals 1 to the length of t. So this time we know how many loops we need to do. We need to do one for every single time step. So remember, if we have a look at our t variable, it's got a bunch of different ones, and we know how long it is. We need a different value for each one. So we use k for that. We're going to do the red dot equals plot a k comma 1, a k comma 2. So this is variable indexing. So the first column for the value of k. So k starts at 1, it goes all the way through. So we're going 1, 2, 3, 4, 5, and so on, all the way through every single row of this A matrix, or this A array, until we get to the end. We're going to use a black circle by the looks of it. You can use ellipses, 3 dots to break statements across pages if they're getting really long. Marker face color red, R for red, and then marker size 6. Pretty clear what marker size does. Frame equals get frame. That's an inbuilt function, get frame. So we don't really need to worry about what that does. We just know that it does what it needs to do. And then write video file frame. So it's gotten a frame, stored it in frame, and then we're going to write it to video file. Pause dt. You can have a look at the help page for pause and see what that does if you like, and then delete red dot because we want to get rid of it after we've written it, ready to write the next one. End for our loop, and then close out the file as well. Okay. So let's see what happens when I run this code now. Okay, so I see a red dot there, but I've come up with an error here. It said unrecognized function of variable red dot. Obviously I've made a typo somewhere. Yep, see, I've called it just red here. Should be red dot. And because when I tried to delete it, it wasn't actually made. So always take note of your error messages. Let's do that again. See what happens. Okay. I get another error. Frame must be 868 by 685. Now that is a Strange error, does it come up again? Okay, so if I move the plot around, it gets a bit finicky. It's actually coming up on my other monitor. So hopefully if you've got to that stage, you see a plot with a red dot zipping around it. Anyone managed to get up to that stage? I've got it on my screen, but it's just coming up on the wrong window, and if I move it over, it yeah, awesome, yeah, perfect. And hopefully you'll see, if it's working correctly, a video being created over in your workspace. So myanimationvideo.avi should be coming up, and then you can just play that back as a normal video as you need to. I remember I came across, if any of you are on Mac, I had an issue with actually playing AVIs. So I had to change some of the encoding to get it to work as a MP4. So if you're having those troubles, yeah, just be aware. You might want to replace the video file, video writer line with something that looks like this to get it to create MP4s. And that worked for me on Mac. You may or may not be in the same situation as me where the AVI wasn't playing properly. So just be aware. Not everything is MATLAB's fault. It's just trying its best, but yeah, often, you know, specific releases of computers, if you're starting to interact with file systems and things like that, can get a bit finicky. So yeah, hopefully you've all managed to create that animation. It's super satisfying. I love it when stuff like that works. And if you're really keen, I'm going to open it up for questions and sort of finish the presentation sort of about now. If you're really keen, you can try and define this Lorenz system, which is another dynamical system, except there's three coupled systems of equations here. And you need to define the parameters, defining your sort of function handle that defines the system will look slightly different, but it'll be really similar. And the code that creates the video will look pretty similar as well, but slightly different because we're plotting three different variables, x1, x2, and x3, or x, y, and z, sorry. I'm going to need to figure out how to display those, how to sort of how to get the plot looking nice. But yeah, give it a shot. It's nice and satisfying when that one works as well. All right, so I think we might call it there. There's a lot of MATLAB that we haven't touched on. If you're interested, come along to my advanced MATLAB workshop. That'll be coming up in 2 weeks. So next week is Simulink, another really important sort of additional thing for MATLAB called Simulink. Certainly you use it in a lot of stuff. Signals and systems I used it in, and control systems I used it in are the two that I've specifically used Simulink in. Jeff, I don't know if you're around still, or you can shed light of any other undergrad subjects that have Simulink components in them. Yeah, yeah. Certainly pops up a lot though.
Yeah.
And
Things like occasionally you get a lot of it.
yeah,
Like small components.
exactly.
Oh, that's cool.
Yeah, so I've thrown together a Simulink workshop for next week. I think it's pretty fun. It's a love-hate relationship with Simulink, I think. If you're really analytical minded, like my undergraduate was physics, so I was used to solving a lot of stuff by hand, full analytical solutions, and sort of a last resort was numerical solutions. Simulink just throws analytical solutions out the window and just says, I'm going to crunch the numbers and you know, sort of numerically, and that's the answer. So yeah, bit different from pen on paper math, but you can do a lot of cool stuff with it. So Simulink's next week, and then yeah, if you're interested in MATLAB, come along as well to the advanced MATLAB workshop for the week after that, which will touch on some of this stuff mentioned here and some other things for yeah, really getting deep into the MATLAB type stuff, which should be pretty interesting. Yeah, any questions? Thanks so much for coming along. Really appreciate it. So yeah, given the amount of recordings that were requested, I was going to be probably presenting this anyway. but it's nice to have actually a couple of people to present to. So yeah, thanks so much, and hopefully we'll see you in the coming weeks, and certainly MATLAB centered for the next couple, and yeah, beyond that, keep an eye out for the other sort of workshops that we've got. Really keen to be presenting them. I like it. I like teaching people things, so the more people around the better. Tell your friends. Any clues of where to look? Yeah, it's really subtle. I think I wrote the code the first time. I went, oh, this is great, and then sort of went, oh, maybe that could be an issue. I think about the statement of all rows and all columns must sum to the same value, and then how I'm checking that in that code, particularly between columns and rows. Now, I'm not sure whether it's actually mathematically possible for it to be wrong in the way that I've written it, but certainly I haven't proved the contrary. So yeah, it'd be interesting if anyone wants to have a try. But yeah, it's got to do with the whether the rows are magic by summing to the same value, or whether the columns are magic to summing to the same value, and exactly how we go about checking that. So that's sort of the hint for that. Yeah, exactly right. I'm checking that there's only one unique element in the sums. So for example, my rows, they could all sum to 15, and they collapse down to saying, yeah, my rows are magic, they all sum to the one number. And then my columns I check separately. I say, do all my columns sum to the one number? And I say, yes, but maybe the columns sum to like 10 and the rows sum to 15. I don't know, like I don't know whether that's mathematically possible to, you know, in the way that it works, or whether you're going to catch the error in the rows check or the columns check, but it's sort of subtle. And yeah, there'd certainly be a way to, yeah, exactly, certainly be a way to sort of check it in code, and potentially if you wanted to prove it, you could, but yeah, pure maths, not for me, at least at the moment. Yeah, good one. All right, well, I'll leave it there and hope to see you next week. And yeah, tell your friends, come along, and stay tuned for the, I'll release the recording at some point once it gets processed. Cheers, everyone. Catch you later. No worries.